Hello, everyone. I am Jelena from MDPI, and I will be your host for today. Welcome to the webinar, Development of Intelligent Robots and Advanced Materials, organized by MDPI and the journal Micromachines. Before introducing the MDPI journal, Micromachines, and the lineup of today's event, I would like to remind everyone that this webinar is being recorded, and the recording will be made available as soon as possible on the webinar's webpage. Please note that you need to be logged into the Sci forum in order to see the recordings. A little bit about MDPI. A pioneer in scholarly open access publishing, MDPI has supported academic communities since 1996. Based in Basel, Switzerland, MDPI has the mission to foster open scientific exchange in all forms across all disciplines. Our 502 diverse and open access journals, including 493 peer-reviewed journals and 9 conference journals, are supported by more than 115,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors. Micromachines, the host journal for today's webinar, is a peer-reviewed open access journal on the science and technology of small structures, devices, and systems, published monthly online by MDPI. Here is the overview of today's program. There will be 2 presentations today of around 25 to 30 minutes each. The presentations are followed by questions and answers session, which will be moderated by our webinar's chair. If you are interested in submitting your research to special issues that are linked to this topic, please visit the website for more information. These would be the 2 currently open special issues related to this topic. Very important, if you have any questions for speakers, please feel free to post them at any time in the Q&A box. So you can find it in the Zoom menu bar at the bottom of your screen, and it would be great if you can post your questions there and not in the chat panel. So the speakers and the panelists can actually answer them properly. It would also be good that you note to whom you are actually making your question. Today's webinar is chaired by Dr. Yinyin Bao, an associate professor of polymer chemistry at the University of Helsinki. He earned his PhD in polymer chemistry from the University of Science and Technology of China, following a bachelor's degree in macromolecular materials and engineering. His research focuses on the application of polymer chemistry in biomedicine and optoelectronics, including light-emitting materials, drug delivery systems, and 3D printed medical devices. Dr. Bao has held senior research and leadership positions at ETH Zurich, University of Paris SUD, and Catholic University of Leuven, and has led research groups as a senior scientist and group leader. He has published over 50 peer-reviewed papers with more than 2,500 citations and serves as an invited reviewer for leading journals in the field. His contributions have been recognized with numerous honors, including being named in 2025 among Stanford University's World Top 2% Scientists and ACS's Rising Stars in Polymers. He also received a Marie Curie Intra-European Fellowship. Our first speaker for today is Dr. Hao Zeng, tenure track associate professor of soft matter robotics at Tampere University and an Academy Research Fellow of the Academy of Finland. He holds a PhD in atomic and molecular photonics from the European Laboratory for Nonlinear Spectroscopy from University of Florence. His research lies at the intersection of physics, soft mechanics, and materials engineering, with a focus on light-responsive and stimuli-responsive materials for soft robotics. Today, he will deliver a lecture titled Non-Equilibrium: What Ciliary Motors, Sausages, and Light-Driven Polymers Have in Common. Our second speaker is Dr. Minghan Hu, a senior scientist and group leader in the Department of Mechanical and Process Engineering at ETH Zurich. He earned his PhD in chemistry from the Max Planck Institute for Polymer Research in Mainz. After postdoctoral research, Dr. Hu established his group in 2024. His research focuses on advancing soft materials into intelligent micromachines with a strong emphasis on biomedical applications. Today, he will deliver a lecture titled Intelligent Microrobots Made from Colloidal Assemblies. That would be all from me today. I will give the floor to our chair, Dr. Bao. Thank you for chairing today's webinar.
Okay, thank you very much, Yanana. I think you pronounced very well the names of two excellent speakers from ETH Zurich and also Tampere University. I think you basically introduced most of the things of the both speakers, so I don't need to speak much about them. But for the first speaker, Professor Hao Zeng from Tampere University, I want to emphasize his ERC starting grant awardee that was very prestigious grant from European Research Council. So he will be the first speaker giving the talk about this non-equilibrium, what ciliary motors, sausages, and light-driven polymers have in common. So the floor is yours, Professor Zeng.
Thanks for the introduction. Are you sure we don't need to fix to the schedule? Because we have still 10 minutes for the introduction.
I think we don't need to stick to the Swiss time.
Yeah,
we are from different backgrounds.
You can go ahead.
Okay. So I will slowly start my presentation. The first thing I need to do is to find the button to share the right screen. As chairman, Yinyin,
yes.
Yeah, perfect. Everything looks fine. So the stage is mine, so I will start, right?
Sure, go ahead.
Thank you so much. Thanks, Yinyin and the MDPI for the invitation. I think they have done very excellent advertisement of this webinar, especially in the Chinese media, WeChat or something. I expect there are many people watching us, but although I cannot see their faces, so this makes me very nervous. I don't know who they are. I promise to give you a very relaxing, very funny presentation, because for the majority of the Chinese in the Chinese mainland, they are going to sleep, right? So I'm not going to show equation. And so in case my friends are in front of the cameras, in front of the computer, then maybe I can name few names. For example, Li Chuang, Li Dengfeng, Guo Yubin, Hu Yin, in case they are listening my talk, so I wake them up. Yeah. So today, a little bit, I will play the movie to warm up a little bit. So the talk is about biomimetics and the micro robots. So this is an example I took from the YouTube channel. Is the flagella or the cilia motor structure, very small, nanometer scale, and is so intelligent. It can help the bacteria to swim inside the liquid, and the structure is so efficient. We consider this is the motor with the best efficiency, and the human being will never reach this level. So in my talk, I'm going to tell how to use the sources to make this kind of structure. So my talk title is what is in common between these three very different things: the flagella or the cilia motor, the light responsive material or light responsive polymer, the field I'm working on, and the sausage. The sausage, the food we love every day. So before going deeper into this topic, I would like to thank my group, the Light Robots group in Tampere University. And they are the people coming for me to have excellent research result, to make the excellent humor for science. So in this talk, the main results are mainly achieved by these three guys. Yu, our undergraduate student, Zhishen and Jianfeng. Both of them recently graduated from their PhD. I want to show their pictures here because they are young people, they need more motivation, more promotion. So in order to remember them, I will give each of them the specific name. Yu is our sauna name. Later, I will come back to this to explain you why he is our best sauna man. And Zhishen is making a lot of swimming robots. We call him Swimming Man, and Jianfeng is our Flying Man. Okay, the cilium. You may also call it flagella if the structure is very long. So it's a flagellum. If it's some bacteria has one tail to swim, some they will choose two tails, or many of them, so with a much shorter length. So people call it cilium, and they will couple, they will have some chowing weight motion. And so typically they need to consume the chemical energy. There are some chemical reaction inside. The system is far from equilibrium because it's alive, it's not dead. It must be far from equilibrium. Fully autonomous because there's not a human being to control the motion. And technically, the motion is non-reciprocal. It's not forward, backward, it's non-reciprocal. There's a stroke pattern. And they can be coupled between two cilium. Coupling between many of them, we generate a chowing wave we call the metachloral wave. And this is the way the bacteria, they build up the intelligence, like the tropism. They swim towards the light or towards some chemical gradient. They need to find the food. Many of them can connect to interact. There's some connective behavior. It's the intelligence, it's the way they build up their intelligence. Of course, it will be very complicated, and I'm not that professional, and I have no hope to understand all the mechanism behind. So what we are going to try is just make an artificial one. Using our knowledge, the light-driven material or light-driven polymers. So what happened in this kind of material? The typical material we are using is liquid crystal. So everyone understands liquid crystal, so common, right? It has a liquid crystalline phase, which at some temperature, all the molecules, they stand one by one in a good order. If you increase the temperature, it undergoes phase transition and becomes disorder. So what we did here is that in each molecule, we add the covalence bond. Actually, we don't need to do the chemical reaction. We just buy the molecule from the company. There are some company that can give you this kind of molecule, can sell you this kind of molecule with a lot of tens of different options. And we add the initiator, we start the photopolymerization process, and each molecule, they will just connect to each other. And then it is not liquid crystal, it's not liquid anymore, it becomes a solid. Since it becomes a solid, it has a shape, but still, preserve the liquid crystalline property, which means if you heat up the temperature, you heat up the structure, it becomes disorder and it will contract along the alignment direction, which is the liquid crystalline orientation direction, and expand to other two directions. And in this way, we can use the light heating or heating to control the deformation, and we call this material liquid crystalline elastomer. So we apply the stimulus, deform, and then we are going to make the cilium. A very easy way to make it is that we just shine different laser beam onto the structure. For example, we can have 4 laser beams shooting on one strip of the elastomer fiber. We turn on, turn off each laser beam with like 90-degree phase delay, and it will move like a cilia underwater. But in my opinion, this is not a model of cilium because this is still control. You are using the on-off light field to control the structure, and it's not autonomous. It's out of equilibrium, but not that far from equilibrium. I will call this is not a cilium. Well, many people will feel unhappy because if I call their cilium, it's not the cilium, but this is absolutely safe because the paper just came out recently from our group and with our collaborator. So Yasman, our first author, she will be happy about it. So how to make the cilium? We use light to induce deformation. It must involve feedback, because feedback is a very important concept in biology. So what does feedback mean? One simple example. If you have a strip of the responsive material, you have the strip and it bends under the light illumination. The light is shining from the side. You shine the light, the material bends. So what you can expect is that if you increase the light intensity, the light energy, more light energy, you have bigger deformation. But once the strip bends, it blocks the light. It reduced the light absorbing area. So due to the deformation, it actually reduced the energy intake. So you may guess that there should be one middle position that it is settled. Maybe half of the light will be absorbed, half of the light will be just passing through. So there should be one equilibrium position. But in fact, not. It does not want to stop. It will keep oscillating around the middle position. And it self-oscillates. I needed to emphasize this more, and I show you another example to demonstrate the concept in a more clear way. Material, any kind of material, hydrogel or liquid crystalline elastomer, any kind of material can deform. You put something on top, a buffer, a structure to block the light. And you shine the light. At the beginning, nothing will happen because the light will propagate and hit the material, and the material will deform, bends down, and the buffer will cut off the light, negative feedback. The material introduces negative feedback to the light absorbing system, and if the light intensity reaches some certain level, if it is enough, it oscillates. So you have the artificial cilium can oscillate forward, backward, and then you may ask me, oh, it's not the same because in nature the cilium performs in a non-reciprocal manner. Yes, we can also do it. If one laser beam is not sufficient, we can shine 2 laser beams, and we have the same strip, but it oscillates in a non-reciprocal manner. And this is also performed underwater. And you may still not satisfied, all right? You may ask, oh, the cilium is not forward backward, although this is non-reciprocal, but in reality is try to spin around the space. So what the negative feedback gives? Oscillation. Continuously, the structure self-sustain by oscillation or spinning. So feedback is good. It makes the system out of equilibrium, self-oscillate or self-spin, self-rotate. So what to do with the sausage? So it's a philosophical question. Sausage is also a cylindrical structure. It's like a cilia, a little bit fat, big size in diameter, but still similar geometry. If you can notice that the sausage we buy from the market is always a little bit banded. Well, because there are some, during the fabrication, there are some process. But if we bend the sausage by our hand, so what this means, if you see the cross section, you are inducing a strain gradient. You are stretching the outer surface out, but compressing the inner surface a little bit down, but pressed. And there's a strain gradient across the cross section. So what happens if you put it on the pan to cook it? There's a gradient given by the heat. There's a thermal gradient. So the heat will expand the material because of the thermal expansion. If you cook the sausage, it may shrink. It depends on what temperature you have. But there's a thermal gradient, and the thermal gradient will induce strain gradient. These two strain gradients, they are not matching each other absolutely. They are in the perpendicular direction, and it generates a torque that makes the system rolling on the hot plate. And this is called geo-elastic energy mode. You don't need to control the structure, you just put it on the hot plate. Because of these two gradients, it automatically rotates. So where is the feedback? You have the hot pan, you have the cold air, you have the sausage. Once you rotate, the bottom will rotate to the top part to cool down, and the cold part will rotate downward to be heat up. So heat will generate rolling, and rolling will just make it cool on the top, and this is automatic feedback. And the phenomenon will be the similar case. You keep rotating. If you search kitchen experiment sausage, and you find this kind of movie from the YouTube channel, it keep rotating, keep rolling on the hot pan. So it's far from equilibrium, it's autonomous, self-oscillating, but also looks very thick, right? The movie looks very, very thick, according to my physics knowledge. As a physicist and as an experimental scientist, I need to know whether this is thick. So I asked my student, you, to buy 20 different kinds of sausage in the Finnish market and perform the experiment at home in the kitchen. And he found out that actually a lot of sausage, they can rotate. They can self-rotate and oscillate on the hot pan, but with the speed just 10 times slower than the movie you saw from the YouTube channel. Okay, sausage can self-rotate, but what to do with it? Why is it important for our research, right? So if you have good imagination as our group members, you can imagine an infinite long sausage, or no need to be infinite, you just have a very, very long sausage. And you try to close it into a loop to make it into a torus. It's very difficult to make it because it will be costing a lot, and but we can make the ring by using our material, the elastomer material, right? And this is using the liquid crystal elastomer to make the torus, and on top of the hot plate, they will automatically rotate from inside to outside, from inside to outside. And this comes back to the cilium, the story of the cilium. Because 50 years ago, there was an important paper written by Purcell explaining that for bacteria, they need to swim at microscopic length scale. It's pretty difficult. If you have only 1 degree of freedom, like the scallop, you open and close, it's not going to swim because the Reynolds number is so low, and the inertial does not play a role in this length scale. You need to have something non-reciprocal, like the sperm, like this kind of spiral structure to rotate to perform the movement in the non-reciprocal way. And at the same time, he predicts one kind of structure, which is the torus. It can keep rotating in the low Reynolds number condition, it can swim. So 50 years later, our student Zhen did the experiment. This is the first experiment to prove that a torus structure can swim inside very, very viscous liquid. And it's made of glycerin. It's as viscous as the honey. So here what I want to predict is this, a lot of respect to Purcell, to this paper 50 years ago. So here, after 50 years since his paper, a small professor, Dr. Hao Zeng from Finland, Tampere University, would like to propose that food at no Reynolds number, and this is the vision. If you have the sausage torus inside the honey, and we call it marinated inside the honey, in Chinese is 腌制. I would predict that it is going to swim inside the honey. So I told Yinyin about this idea, and Yinyin said this is very ugly. But who knows? Maybe someone would like to try this kind of food, and it may be delicious. Thanks ChatGPT to generate this ugly pictures. Okay, so a little bit conclusion. Cilium, light responsive materials or polymers and sausage, what they have in common. Far from equilibrium, but they can self-oscillate. It's a phenomenon far from equilibrium. Feedback. All of them can make feedback. There are a lot of feedback in biology. It's very difficult to understand, but in our system, the feedback it will be either positive or negative, built by light beam, will be easier to handle. And if we are interested in mechanics, so there will be a zero elastic energy mode for both sausage and the responsive material. And then you can doubt that, oh, for cilium, they are better than the natural cilium because they don't have the zero elastic energy mode. But wait. The author, one of the inventor, Falco and Eagle, invent the zero elastic energy mode. It was a Nature material paper in 2018, right? Ego told me, no, in biology, in the bacteria, in the Flagella motto, the hook, the green color, the green part you see in this figure, it is actually a geoelastic energy mode. So very, very important message from Ego, and I would like to do some advertisement for him. He had a very nice review paper in Archive, and I hope he's also happy that I'm doing this kind of advertisement for him. Okay, I want to end my talk by showing you one movie that is the culture of our group. Yu, here I explain you why Yu is the sauna man, well, the perfect sauna man. And I'm going to play you a movie so you can yeah, it's completely out of equilibrium process in human beings sauna activity. And I got the permission from you to show this movie. So no worries about the copyright. Thanks. Welcome to Finland.
Okay, thank you very much for Hao's excellent talk and the great story about the sauna and the sausage also. But I think the ChatGPT can do better for the image creation. Maybe we can choose another software next time. So now we have the time for questions from the audience. I can see something on the chat and also maybe the Q&A part first.
Yeah, I saw two questions.
Yeah, do you want me to read it for you, or you can just check it?
Well, I can read. So one question is
Okay.
for how is six light-based polymers can be used for building social robots for working with older adults and persons with mental health disability. Thanks. Sumium. Sorry for the pronunciation. Social robot and the elders. The politically correct answer is always maybe, who knows, and yes. So maybe, who knows?
Yeah.
Well, this
But
is
so
very much
what is the
application.
social robot? What is the social robot?
I think what he or she means is the interaction. The robot interact with other people, and some application in healthcare to help the people to stand up, to sit down, and there's some wearable devices to if you have the what the name of that this is, if you shake your hand too much, and there's some device can help you to adjust this. So I think this also means the interface between the robot and the human. So it must be soft robot. So in this sense, the polymer, yes, they can play some role in soft robotics. And then I think the question for me would be, why it should be light? Why should not be pneumatic or dielectric? So Yinyin, next time you can invite other people working in other topic, pneumatic
Maybe we
and
can combine with
dielectric
3D printing.
and 3D printing. And so why light? Yes, I don't think the light based polymer can play a significant role in large scale robot. if you want to make something small and it would be difficult for motor, for those kind of pneumatic actuator to make smaller structure, right? But for polymer, it's very easy to scale it down. You just cut the material into very tiny pieces, and it work at that length scale. If you use 3D printing or laser writing, you can even make smaller structures. And the second question is too long, so I'm not going to read. I don't think it's a question.
Yeah,
So
I would say it
reaching
is
for
not a
collaboration.
question, so I will just leave it there until the end of the webinar in case somebody has any kind of offer for the collaboration, and then we can move on, Dr. Bao, to the second presentation.
Yeah, maybe I just follow one question about the light.
Of course. Yeah.
Like for the design of flying robots or smart robots, like what's the limitation of the light-based mechanism?
I think according to me, I think the biggest drawback or limitation is not that useful. It's funny and is conceptually novel, but if you talk about application and that, or I would say I'm not focusing too much on application. I'm sure many people or other researchers, they have their approach or technical solution for practical applications, but
So in other words, we still have quite a long journey for this kind of robots to be applied in our daily life.
you are a very good chair. Thanks, Yinyin.
Okay, if that's the answer, then we can thank the speaker, Professor Hao Zeng again. Then we can go to the second speaker, Dr. Minghan Hu from ETH Zurich. Because Yelena already introduced his background before, then I will just emphasize that Dr. Minghan Hu is the prestigious Swiss Arizona Fellow funded by the Swiss National Science Foundation. So this is a very important grant program in Switzerland supporting the young researchers to become independent leaders in science. Then he will talk about the intelligent microrobots, especially made from colloidal assemblies. So the floor is yours, Minghan.
Yeah, thank you. Thank you, Yinyin, for the nice introduction. Now I will share my screen. So hello, everyone. I'm Minghan, and good afternoon from Zurich. So as Professor Bao introduced them, so I'm the group leader at ETH. I recently started my group from 2024, and probably you may know the ETH from this is the technical university from in Switzerland, and so as I show the picture here, this is our campus building, the main building, and this is also famous for the Albert Einstein's. We still have one of his cabinets here in this building. If you by chance can visit here, then make sure that you go to this building to visit Einstein's cabinets. And my lab, I recently established, it's in this small building next to it. And this is the picture I took on the 2024 in October with my first PhD student. It's her first day, Ziyu. She started her PhD. Then we set up our microfluidics to start the experiments. Okay, then my research topic is focused on the microfluidics. And the microfluidics is not it's a new topic, but it's actually originally inspired by this fantastic voyage. It's a science fiction in 1916. And in this science fiction, scientists shrink a submarine into the millimeter size and inject this into the human blood vessel. And this submarine can swim to the targeted tumor place to kill the cancer. And of course, in the reality, we cannot shrink a submarine into such a small size. In our microrobots community, scientists always use the top-down strategy to make these intelligence microrobots. The top-down strategy I'm talking about is like 3D printing or the lithography to make these small millimeter or micrometer size microrobots. But today I will tell you another way to make these intelligence microrobots. Instead of using the top-down strategy, I propose to use this bottom-up strategy, which means first we synthesize the nano objects, for example, the nanoparticles or nanocapsules with different functionalities inside, and then we assemble this together with the assembly method to make this intelligence microrobot. Therefore, in my research, so it mainly focuses on the three parts. First is the synthesis of these different nano building blocks or micro building blocks. Then we develop the two different strategies, bottom-up strategy to assemble these building blocks together. One is the evaporation-driven assembly, another is the capillary assembly. And then afterward, we are in the engineering department, so we are more focused on the application side. So we make it with our microsystems with different functionality, including the control release for the biomedical application, and as well as we also show we can control their movements inside the inside very small scales. Precisely control their movement. And we also can do some sensing functions for our micro robots. So first I will introduce to how to use these nano building blocks to realize the sensing function. And for the sensing functions I'm talking about is about the damage sensing. It's not like sense the pH or sense the temperature. Damage sensing is actually from from our human itself. It's very easy to do that. For example, if we got some injuries, then this on our skin will have this bruised area, and this bruised area he used the optical color optical signal to tell us this place is damaged. So then this in this case, our body can know where the damage is, and we know we can visualize where the damage it is. But for the artificial materials or for the robots, it's they cannot see themselves. So it's how can we do that? Then we can use the microcapsule to realize this. And the strategy to do that is we have the microcapsule. It has the core shell structure, and inside the microcapsule we have this liquid core with the filling with the dye, and the dye can be either the like the normal optical dye or the fluorescent dye. And once this microcapsule is broken by the external force, for example, it got the cutting or got hits bendy, and the microcapsule can be broken, and the broken will release the dye inside, and this dye can be active to show the optical signal. And this what we like what we have done previously in 2018. So we made these microcapsules, then we embed it into the polymer coatings, and then we cut it out by introducing damage, and then we can clearly see that the embedded microcapsules place can significantly show the color or where the damage it is. And with this, we can realize the damage sensing by embedding these microcapsules. And if we go back to this bruise again, we can see that actually our human body is very clever. We can see it's not only it's not only show the single color. It does not only show the single color, but it shows the multiple color. the darker part shows the more damaged place. Because for the mechanical events, it's always not a single stress. It's always the multiple stress. In this case, can we use our because we know the real environments are more complicated than just the one type of damage. So we ask ourselves, can we make a system that can sense the multiple stress at once or simultaneously? To do that, we further develop our microcapsule systems so we know the broken of the microcapsule is depending on the shear thickness as well as the diameter of the microcapsules. So we know that if we have the thicker shell, then it's hard to be broken. And with that, we can tune the breaking force of our microcapsules. Then we can encapsulate these different dyes inside to show the different signals depending on the different breaking force. To do that, first we need to synthesize this microcapsule with the different shear thickness and diameter, and we use the microfluidics because microfluidics is a very precise tools to make the droplets with the precise diameters. As I show here, we can nicely tune our microcapsules diameters. Also, we can make it very monodisperse. And by controlling the polymer we use inside our this microfluidic synthesis, we can also further tune the shear thickness of the microcapsules. But with that, we test our microcapsules with different shear thickness and diameters. And then we can nicely see that the breaking force can be tuned by changing the ratios between the shear thickness and the radius. And thanks to the help with the Professor Bao's group, we can have this very nice fluorescent dye with the different emission wavelengths. And then we select the 3 different microcapsules with the different breaking force, encapsulating the dye inside to make this microcapsule with different stress sensing. And the next step would be to test if they can really translate this mechanical signal into this optical signal. So to do that, first we put these different microcapsules with the dye inside these different patterns. So since we are in an ETH, so we just put it into the ETH letters. And then once we apply the different force, the microcapsule should be broken to show the strong fluorescent color. And we did the test. This is what we got. As I show here, we can clearly see when we use the microcapsule with the smallest breaking force, it will be broken and the 3.2 megapascal stress. And when we have for example, this yellow dye, it's encapsulated inside the microcapsule with the higher breaking force microcapsules, and then it will have the higher breaking stress. And with that, we can prove that our microcapsules can nicely translate the mechanical breaking force into the optical signal. But the next step would be how to combine these 3 microcapsules together. And in our lab, we develop a nice capillary assembly technique to do that. It's the capillary assembly. So briefly, we first let the microcapsules suspension to put deposition on the templates, and then we just tune the surfactant concentration as well as the scanning speed. Then we can nicely end up with each trap with 1 microcapsules inside. And with that, we can let it dry then we do the same trick again with another type of microcapsules. Then we can also nicely we can play around the parameter. Then we can let it control like only another single microcapsules deposits inside, as I show in this video and the schematic. And we do it again for the last one. So then we can have the 3 different identical microcapsules inside the traps. Okay, then with that, we can we first also do the breaking test as I did before. Then we can see if there is no microcapsules broken, no applied force, there is no fluorescent signal. If it's only one, and we can see the green signal from the first microcapsules. And if we have a higher force, and we can see the 2 microcapsules broken, and we have the mixed signal between the yellow and green fluorescent color. And if they're all broken by the highest force, then we also have the 3 color. And in this case, we can translate this color tone into this nice to match the different stress range. Then we also further to apply the higher force into the PDMS film. With that, we translate this fluorescent signal into this color map. We can nicely see this gradient color, which shows the different stress precisely show on this broken PDMS film. And so with that, we can so this one we show them we can use the nanoparticle or nanocapsules synthesis, the microcapsule and nanocapsule, while the capillary assembly we realize the sensing functions. And with the same capillary assembly methods, we can also to realize the locomotions. So what I'm talking about now is like we use the capillary assembly. As I mentioned before, we also developed the evaporation-driven assembly technique. And with that, we can also combine the locomotion and the control release function together. So talking about this assembly technique, so it's like playing Lego. We have the building blocks, then we can assemble the different building blocks together to assemble the materials. But we instead of doing it by hands, we do it in the micro scale or in the colloidal scales. In this case, how to control this the assembly process. And the way we use to control the assembly process is we use these droplet templates. So briefly speaking, we have the nanoparticles or nanobuilding blocks inside the droplets. And during the droplets solvent evaporation, these nanoparticles will self-assemble together into the spherical shape to minimize the energy. And with that, because they are making from the nanoparticles, so we call this assembled structure is the supraparticles. And so this is the work from the other group, from the group of Professor Fogger in Erlangen, and they show them they can control the evaporation speed during the assembly process. Then in the end, they can control the nanoparticles assembly structure from a very randomly packing to a crystallized packing. Furthermore, with this technique, we can also break the symmetries into the different shapes. So from the Professor Olin Relief group in US, so they add the sodium chloride, the salt, inside the droplets because the sodium chloride will cause the nanoparticles inside to previously aggregates. Then in the end, they won't end up with the spherical shapes. Instead, they will have this anisotropic shapes. And with that, the anisotropic shape is very interesting for us because we are working on the microrobots because the asymmetric shapes will give us the motion or efficient motion. But with this shape, it's hard to control because it's adding the sorts and the end structure is not that controllable. And we want to have a better control shapes. To realize that, we use the magnetic field to control the shape. To do that, we have the magnetic nanoparticles inside the droplets. Then we put it on the super amphiphobic surface, which will not spread the droplets, but instead it will maintain the spherical shapes. And we can see from this video, during the water evaporation, in the beginning, the droplet will maintain this spherical shape. But with the time, because the magnetic nanoparticles concentration increase, then the magnetic force also increase, so it can break the symmetries to end up with this anisotropic shapes. And with that, we also play around the magnetic particle concentrations as well as the magnetic field strengths. Then we can have we can control the shapes from this cone-like shape to the barrel-like, also the double tower-like shape. And this is very nice. And furthermore, we can also tune the magnetic field orientation to tune also the final shape orientation. And we can also add more components inside. For example, here, what I show here is we can add the titanium dioxide, which can be used for the optical like the photocatalysis to degrade the organic dye. And this we can still, when we have the magnetic nanoparticle more than 15%, we can still make this anisotropic shape. And because they have the magnetic nanoparticle inside, then we can have the very nice magnetic control motion. And here we just use the magnet to write down the P trajectory with our superparticle. And but the next thing we want to like while talking about, I would like to talk about is to make it more or multiple functionalities. And to do that, we instead of using the single nanoparticle as the building block, instead we use the dextran nanocapsules as the building block. Because the nanocapsules can carry the cargoes inside, then we can have more functionality within these cargoes. And here what I show is we use the dextran-based nanocapsules because they are biocompatible. And then we use the microfluidics to generate the droplets. Within the droplet, we have the dextran nanocapsules with different cargoes. And then we do the same trick. We evaporate it then the nanocapsule will self-assemble into this cluster structure. With that, because they are making from the nanocapsules, therefore we call it supercapsules instead of superparticles. And this is the SEN images we can see. They are nicely packed each other. And we also cut it out to see the inner structure. We can see they are fully covered with the different with these nanocapsules. And the nice thing is because we use the microfluidics, we can nicely control the droplet size and also the concentration of our nanocapsules within the droplets. And we can further control the final supercapsule's diameter from 3 micrometer in diameter until around 18 micrometers. And we also encapsulate the two different fluorescent dye. One is the green, one is the red one. And then we can nicely see they are still maintained inside their building blocks. And the next things we do is we also encapsulate to indulge the control local motion functions. We encapsulate the magnetic nanoparticles, iron oxide, inside the nanocapsules. Then we assemble this nanocapsule together to make the magnetic supercapsules. And we can nicely see they still maintain the same magnetic properties. And here what I show is we simply use the magnet to draw the triangle. And this is the single magnetic supercapsules. And here you can see my hand is still a little bit shaky. Yes. Okay, and the furthermore is because we want to we use it for the biomedical application. So we want to see how about the cargo release profile of our supercapsules. We know the simple nanocapsules, they can release dye or the cargoes through the diffusions of the polymer shell. And for our case, the nanocapsules will reach the plateau of the release after 4 hours. And once we compare with our supercapsule, we can see the plateau time will be extended. And with this, we can know then we can have the sustained release of our supercapsule systems. We also do the model analysis based on this fiction model. We can nicely see that this release, the half-life time of the release is follow this fiction model, and which means we can nicely tune the diameter of our supercapsule to further control the release time. And the last things I would like to show here is because this nanocapsule, they are assembled together by the hydrogen bonding and van der Waals force. Once we apply the external force, for example, the ultrasound, these nanocapsules, this supercapsule can be disassembled again into the single nanocapsules. Then in this case, the release profile can be significantly changed, as I show here on the right side. Then in the end, so I would like to summarize. Then we use the different in our research. We use the different synthesis methods to make the nanocapsule or nano building blocks. By applying the two different assembly methods, we can have the intelligence micro scale materials with the different functionality, including the control release, locomotion, and the damage sensing. And of course, we just starting and we have just scratched the surface. We still have a lot to do. And in the end, I would like to thank all of my collaborators as well as my funding from Swiss National Science Foundation. Thanks to for them to support me to start the group. And as you can see, also we are the young and very dynamic group, and there is a lot more coming soon. If you are interested in microrobotics, I encourage you to keep an eye on our fantastic voyage. And thank you, and I look forward for the discussion.
Thank you very much, Minghan, for the nice presentation on colloid assemblies-based intelligent microrobots. And you have a very nice big group, actually. So now we have time for questions from the audience. But I don't see anything from the Q&A yet. Seems the audience are a bit shy.
Is that true that you have such big group in ETH?
I mean, so now currently, as I show it in the beginning, we have one PhD student, and the others are the graduate and undergraduate students. Yeah.
So you
only
don't
one
need to cover
PhD.
the budget.
No. In Switzerland, people are very expensive. Yeah.
So he has self-funded researchers. That's very good. Maybe I can give a questions first in case some people want to give later. Like for your if you want to use the microcapsules to apply as the part of the soft robotics, how is the stability or reusability of these microcapsules? Because maybe for robotics you need them to be durable.
Yes. Thanks for the questions. Yes. So for the microcapsule, once we assemble them together, they are made so the force, only the physical force, so the hydrogen bonding and the van der Waals force. So it can be interrupted by the external force. For example, the ionic strength. For example, in the human being, so the blood has a very high ionic strength. It could also affect the assembly structure or the stability of our microrobots. And what we can do, or what we are doing now is we also introduce the further chemically cross-linking bonding to link this microcapsule together after assembly. So then they are they are more stable in the for the biomedical application. Yeah, that's our current solution. Yeah.
Perfect.
Mm.
So I still don't see any questions from the audience. If there are no any other questions, I would like to thank two speakers again. Thanks for their very nice work. One topic is on the liquid crystal elastomers based on intelligent robots, and the other is colloidal assembly based intelligent microrobots. So we can see the importance of the advanced materials in the role of design the future robotics. And I think this webinar is a very good platform for demonstrate these nice works. Thank you very much. So I don't know if any other people want to say something.
Only me, I guess. So thank you all for being a part of this webinar. Thank you, Dr. Bao, for chairing it, and Dr. Zeng and Dr. Hu for giving such wonderful lectures. I hope everybody enjoyed. As I mentioned at the beginning, recording will be available in a few days, maybe weeks after we edit it, and you will be able to access it on the webinars page if you are logged into your site profile. That would be all then from us for today. Once again, thank you so much, and hopefully we will have another project soon for you.